Okay, so I hope my screen is visible to all of you. And
Yes, sir.
this is the problem. This is the first problem. Find the SVT for the matrix A, where we have to first find the A transpose A. So all of you try it and let me know what is going to be A transpose A.
Ten, 20, 20, 40.
Sir, 10, 20, 20, 40.
10, 20, 20, 40. Yeah, this is just a multiplication. We have already many times doing the matrix multiplication, so this is a simple one. Presenting, I'm not able to see response. Okay, this is 10, 20, 20, 40. Okay, what is the next? Okay, calculate the eigenvalues of it. Anyone can tell directly that eigenvalue is going to be 0 or not? No? 10, 20, 20, 40. May not be on.
Sir, the iron values are 0 and 7.
0 and 7. So anyone can tell without like just looking the answer, like just seeing it, and can the eigenvalue is 0, can give me the reason? Anyone? Here, if I am
Well,
see it
because
here,
AC is equal to B square, so eigenvalue is 0.
is sorry,
AC is equal to B square. Right?
A
20 into 20
and
is 400 and 10 into 40 is 400. So AC is equal to B square means lambda is 0.
He means that a determinant is 0.
determinant is 0. Okay. Any other reason?
Is that okay, sir? AC is B square equal means the lambda should be 0.
Yes.
They
I just
are
want,
linearly dependent.
yeah, this is a good answer because I will say the good answer. The reason is if the matrix is big, in that case we are always not able to find the eigenvalue. So the determinant. So the best case is, let's see the dependency of the rows. So here the first, if you see
Second
here
row is
second
twice
row,
of first.
yeah, twice of first row. So in this case, if you know the property of getting determinant, if you, in this case it is a singular matrix. The best answer is singular means 0 is going to be the one eigenvalue, means determinant is going to be 0. So this is the case of for big matrix, but the both of you are correct answered it.
Sir, the iron values are 0 and 5. I calculated previously values of E.
So eigenvalues are 0 and 50, not 5.
Yes, sir.
Yeah, okay. So last time even I was saying no, if it is a 0, then what is going to be in this case? So we'll see there. This is a very, very good problem to see the way we have seen the three cases there to step by step. If it is 0, if it is non-zero, and if it is 0, then we have seen two ways of solution. So here, let's see. So as we see here, the eigenvalues is 0 and one eigenvalue is 50. So the middle part, the sigma, the matrix now is going to be just root of both. We'll take the root of both and we'll keep on the diagonals. So this is going to be, this is a square matrix. So it's look like we'll keeping on diagonal. Otherwise, we'll start from the first entry and not diagonally means a kind of will come like A11, A22, A233, like this will come. Okay,
Bigger,
so this
bigger,
is
bigger lambda will be first, no?
bigger lambda would be the first one, increasing one. Sorry, decreasing one. No?
Decreasing one.
So this is the sigma. Next is okay. So see that now the changes. Okay, but no. So first calculate the eigenvector. So what are the eigenvector is going to be this matrix? This matrix set. All of you try it. I think no answer is given here. That's why it is happening. Let's see that.
There is no box to give any responses.
So is it 1 by root 5 and 2 by root 5?
Two by root 5 and 1 by root 5.
2 by root. Okay.
Where to answer it? Peer deck is working.
Yeah, no. Then yeah, actually,
Okay, okay.
because this is RC. Yeah, so the final thing is a matrix, but we are solving in a stepwise.
Okay, okay. It is better. It is better to do that.
So let's see that what are the eigenvectors we have. So eigenvectors of for 50. Yeah, so
Is it 1 by
x1
root 5
is
and 2 by root 5, sir?
2 by root 5.
Eigenvector?
Here is we
So
are
for
getting
50, I got 1 and 2.
1 and
Other
2.
one is
So this is correct. This is
And
correct. 1
for
and 2.
1 by root 5 and 2 by
0, for 0, I got -1 -1 by 2.
-1 and -1. That is also correct. If you just divide by 2 both, it means vector, it is going to be -1 and 1 by 2. So how others are getting root is there? How root is coming?
They're taking unit vector.
Unit vector, no?
Okay, unit vector. Sorry. Yes. Yeah. So we have to normalize it. This is a
So
symmetric
why
matrix.
we have to normalize?
Normalizing is in the this is it is in the algorithm. Or the second thing is, if you see the proof, in proof there we last time we are seen, right, norm is going to be the lambda times something is written there, so only we are getting lambda. So something in the proof, the reason is in the proof. Last time we were looking that. And sometimes no simple reason is, whenever we have vector, if you have a vector, then just need the direction. So to know the direction, we generally normalize it. If you just divide by the normalize, means we just divide with the norm. It will be a unit vector. That's all. So it makes easier, to calculation sometimes. In theory part generally. And here we'll get the the both vector, no, the P and Q, or sorry, Q1 and Q2. Those matrices are going to be orthonormal. That is another reason. Okay, so we can construct Q2. So let me do it the head here. Just need to keep. So normalize the eigenvector and the
What was n
A
in that
transpose.
in our equation? N A transpose A. And what is n?
Where is that n?
N. Last. Go back. Yeah, here n A transpose A means capital
Where
N.
is?
Capital N.
Oh, sorry. This is null space. This.
Hmm.
This is telling the null space means finding the eigenvector means we used to find the null space of this matrix. That is what, no?
Hmm. Null space of A transpose A, na? So how did we got
A trans
to
not null space of A transpose. A null space. See, this is a step to find the eigenvector. So in the way of finding, if you are solving the equation, what you are doing, you are finding the null space. That's all. This A transpose A minus lambda. This is the equation, right? You have some
Hmm.
system of linear equation. You used to get the system of linear equation from this portion. So you are solving actually you are finding the null space of this whole matrix here to here. Getting?
Yeah.
Not getting.
10, 20,
Yes.
20, 40 was the A transpose A, na? So we have to
Hmm.
subtract 50
Yes.
in 10 only, na?
In 10 only, huh?
Then it will come,
Yes.
na? 0.5, right?
Yes. Yes.
Okay.
So that is in null space. That is called the null space. Means we are finding the null space of that. Solving finding the eigenvector means we are getting the null space of this A trans means here for any vector.
Right.
Mean to
Yeah.
say,
Okay. Thank you.
getting, no?
Yeah, good.
So the mean to say, if you want to find the eigenvector for a matrix A, means suppose lambda is eigenvalue. So we used to solve like this.
Yeah.
Means n equal to 0. So this is
But
called
AX
find the
minus
null
lambda X
space.
AX minus lambda X is equal to 0. They're the same.
We are actually trying to find the null space of it.
Hmm.
So here I think there is a typo. Then that's why it is happening. Here it is. It should not equal to 0. Just writing to the null space. There is no mean of writing
Yeah,
equal
it
to
should be
0.
null space, right?
Just this should be null space of this. Means here a minus lambda I and x1, x and y equal to 0.
Right.
This implies this.
Right. Okay.
So this is the thing. Now if we construct Q2, so Q2 is going to be this one. Just divide by then normalize it and we fill it then Q2. Now we have to find Q1.
So
Q2
how to
beta.
calculate Q2?
So Q2 is just writing the vectors in as the column wise. If you see, this is the first eigenvector, this is the second eigenvector. That's all. See it, you already said no, -2 and 1. And normalize it, this is what you will get. So I just wrote the eigenvector. This is first eigenvector, this is second eigenvector.
Only normalized portion is this, huh?
Normalized one.
Okay. In the decimal form, okay.
This is what you see. We got okay. We got 2 and 1 and -1 and 2, right? So if you just divide, this is going to be √5 and this is √5. This is our first eigenvector, this is second eigenvector. So Q2 is going to be 2 1, sorry 2 1 means writing to be 1 upon √5. 2 1 means here. Okay, so let me make it out. Best thing is
So
√5 is
-2, 1 and 1 and 2.
-2 and 1.
Yes, sir. And 1 and 2.
But what was the eigenvector? 0.51, no?
No. What are the eigenvectors all of you got? V1 is what?
-2, 1.
-2 and 1. And the second one,
1 and 2.
1 and 2. Okay. Okay, this is eigenvector. This one is I wrongly wrote. So Q2 is now, we just write it 2, 1, 1, 2. Okay, but I want to write in the normalized one, means I can normally, means here the norm of this vector is root 5, this vector is root 5. So here directly write root 5, or you don't want, this is root 5, this is root 5 here. This is root 5, this is root 5. This is your Q2. I just wrote the vector column wise, eigenvector column wise. So I think this is our second, right? This is the second one. This one is considered for, because this is for 0, no? This is for 0 and this is for root 50. So this will be in the first column and the second one. So this will be here. Root 5, 2 upon root 5, minus 2 upon root 5, and 1 upon root 5. Okay, this is our Q2.
First,
Q2
we have to
transfer.
look at the bigger one, then bigger
Yes.
bigger vector.
Yes.
Yeah.
Because this is of, I think this is of root 50. Sorry, this is of eigenvalue 50.
Yeah, this is for
Right?
50. This is for 50.
So what was the answer given?
This is the answer. So it is written in the decimal form.
So in points minus
Point.
0.89.
This is what.
So can you show me the earlier your working, that your board?
Yeah, this one.
So if we wrote like eigenvectors of 0 first and then eigenvectors of 50, is there any problem?
Yeah, actually it is, and in algorithm it is, we used to keep the algorithm means in proof or in the form of itself, in SVT form. The first one is bigger one, I think, correct? And the second one is, means in the decreasing form it we should to keep.
Sir, can you take it slightly up, the other handwritten board slightly?
That one
Yeah.
is the wrong one.
Okay.
Why I can't take V1 as 50 and V2 as 0? Can I not interchange it?
V1 is 50 and, sorry, V1 is 50. What is the confusion here? I don't know. Like, this is the eigenvector of 0 and this is the eigenvector of 50. So why I am keeping it? So what we will do, will sigma we wrote, okay, sigma, okay, don't. So sigma we wrote in this fashion, root 50 and 0. Okay, this is our sigma. So I just keep it here 50. So the first column of Q2, first column here, the Q2 is here, no? Q2 transfer. So first column of Q2 is going to be the eigenvector for 50. So this is here. Eigenvector for 50 is this one, right? No, not this one. This one. So 1 and 2, and normalized form is this one. Now here is our 0 rule, eigenvalue 0, 1. So we'll second column with the second eigenvector, for means of 0 eigenvector. So this is here. So this is minus 2 and 1. So normalized form is this one. That's all.
Okay.
Okay. Is it clear? Why I am writing the first one?
Yes, sir, yes.
Yes, sir.
We were confusing with the order only, because the first
Okay,
order
so,
is required to the bigger one, then we have to
Uh-huh.
go to that.
If it is in swapping form, there is no issue, but means here just keep the proper order here. This one is, if it is you are writing 0 here and here is 50. So according to that, you just keep the
Order
this.
is required. Order is required.
Okay. So if order is required, if it is already mentioned, yeah, I have seen also. So order is already mentioned. So let's keep that, and we can let's keep first one is 50 and the second one is here is 0.
A decimal part is just conversion of this 1 by root 5, no?
Huh.
Yes. Okay, fine.
Okay, let's do the next one.
Write 1 by root 5 in decimal?
No, not necessary. Yeah, here is it's depend on if it is in the option wise is asked. In option it is mentioned, then you have to do, otherwise no need to do.
Otherwise not required, right? I mean, for computationally, root feels much organic.
Yes.
Let's
construct
Q2 transpose, actually, I'm getting the opposite, actually. So is it because of which one vector to be written first, V1 or V2, if I do this way? Lambda 50 has to be written first, na?
Lambda 50. Yes.
Yeah, so dear, lambda 50 is coming out to be Q2 curve is coming out to be 1 by root 5, 2 by root 5. Am I right?
What we wrote is only the
1 by root 5 by 2 by root 5.
Not Q2 transpose.
Yeah, so if you go up, sir, actually, slightly up, yes, slightly. So Q, so this is corresponding to your handwritten one, the one. Yeah. So we corresponding to this is 1 and 2. So your V1 should be plus 1 by root 5, 2 by root 5, isn't it? So if you transpose it, then it will become 2 by root 5 will go up, na?
Yeah.
And minus 2 by root 5 should go down, na?
Correct.
So it is just going opposite, actually.
Correct.
So Q2 should be 1 by root 5 by minus 2 by root 5.
1 by root 5 and then minus 2 by root
1 by root 5.
Okay. So yeah, so means Q2 is, if you just want to find the Q2, then do the transpose of it.
Yes. So this one is this one you did it for Q2, na? This what we calculated now?
Q2 transpose.
Q2 transpose. What I'm saying is, sir, Q2 is 1 by root 5 and 2 by root 5, isn't it? Yeah,
Yes.
2 by root 5. If you transpose it, then minus will go down. Minus.
Yes.
But in your this thing, minus was not there, so it was plus.
No, here it is, no?
The other one. Yeah, this one transpose should be minus 2 by root 5, na? At the bottom.
See, I constructed this for transpose one. So this is for transpose one. Q2 transpose is this one. If you want to Q2, then you have to do just transpose of it. This is what. If you
take the eigenvector, so that should be Q2, na, sir? That should be Q2.
That should be Q2.
Yes, whatever eigenvector we have made, that is V1 is 1 by root 5, 2 by root 5. 1 by root 5, 2 by root 5 is say V1, and minus 2 by root 5 and 1 by root 5. These are the two vectors for the Q2. Yes.
Just a second. Okay, so that is okay. Just a second. Okay. Okay, if this is the confusion one. Okay, just a second. Okay. Okay, this is okay. You use the eigenvectors. Okay. And the transpose. Okay. So, okay, so this is for Q2.
Yes.
I just missed it. So this is Q2.
Yes. This is Q2, And if you transpose it, minus 2 by root 5 will go down,
and
Q2 transpose will be.
finally Q2 transpose is.
Yeah, this sign will change. 1 by root 5 by minus 2 by root 5, and 2 by root 5 by 1 by root 5. Yes.
Yeah. Okay. Yes. As we used to do in this is a square matrix, so diagonalizability. Okay.
So 1 by root 5, no?
1 by
In
root 5.
first row.
Yes. So yeah, so whatever the eigenvectors will get, okay. So let me, many of you got confusion, okay. So let's say we formed sigma. So let's keep as algorithm that okay we are doing like this. The algorithm is we first find the sigma where the first is going to the bigger one, okay, and everywhere is 0, and the second one here is going to be our 0 eigenvalue. This is our sigma. Now we'll construct Q2. So Q2 is going to be the normalized eigenvector. So normalized eigenvector is going to be, so as we got, first we'll write for 50. So for 50 eigenvector is this one. Okay, so let's keep it here. So 1 and 2. Okay, and normalized form is just root by 5, and this is. And the second eigenvector will keep it here for 0. So because 0 is here, so this is this one. So minus 2 and 1, and normalized form is this one. Okay, this is our Q2. Yeah, I just missed that. Okay, so this is our Q2. This is how we'll form. And now we'll construct. Okay.
So Q2 is basically the eigenvalue is greatest. That was first eigenvector we have to write, and the second the lowest vector.
Sorry.
We have to first write for biggest eigenvalue of vectors.
Yes. Okay, let's construct Q2. Sorry, Q1. So Q1 is this way we'll follow. This is the step to follow, right? 1 upon sigma A x1. Okay. Sigma 1 upon sigma 1 A, the vector, eigenvector x1. So we will do for 50. So see the steps. So okay, so okay. Let me all of you do first. Okay. So without doing this point, just all of you try it and let me know what is going to be the Q2. Sorry, Q1. All of you try it.
Last slide, sir, please. What was that?
This one, I just if I will tell, then
which one we should follow? This 1 by sigma 1 A star.
So that is what. So all of you first try.
Okay.
All of you first try. Just construct Q1. Whatever you know, let's just construct.
Question,
All of you
please.
try. Sorry.
So the question, please.
Question is need to construct Q1. We have already constructed Q2. So we want to construct.
I want to write down the question. I joined a little late.
Okay. So question is, we have a matrix. This one 1 2 3 6. Okay, and we are actually trying to find the SVD form. That's all. So we have constructed Q2. Now we are constructing, means we have found Q2, and now we are finding Q1.
Coffee lena hai? Huh?
Okay, so all of you try. Just doubt. Let whatever the doubts is coming in your mind, let them come. Okay, We'll see.
It is same as Q2. So formula is here. So if you see what to find Q1, we used to do this formula 1 upon sigma 1. Sigma 1 is already singular values, and this is A and star x1 means whatever the eigenvector for 50 sigma for 50 we are doing. So the matrix time and the normalized eigenvector. This is we will get. If you do matrix multiplication, this we will get. Okay. But what we will do for 0? Now we want to find the y2, right? Is it? Is it correct?
Yes, sir.
So for 0 we have to do. So, but see, for 0 there's a problem. We cannot do this one. This formula cannot do, because how we'll do 1 upon 0? How what value will get? This is undefined.
How, sir, how did you get this 1, 3, 2, 6? That A was 10, 20, 30, 20, 40, no?
No, that is your A
That is
transpose.
A transpose.
No. Acha. So initially A was given 1, 2, 3, 6.
Yes.
Okay. 1, 2, 3, 6. I have not seen. Okay.
So this is what you will get. So 0 is a big issue. So how we'll do? In this case, now remember last time what I said? Just find a vector which is orthonormal to the vector. This is what we are doing. So we have, sorry, this y2. So y2 we want orthonormal, which is orthonormal to y1. So y1 is this one.
This star is the multiplication sign here, no?
Here is the star is multiplication sign.
Multiplication sign.
Yeah. So this is what. So y2 is, see that y2 I am choosing which is orthonormal to y1. We have y1 found here. And that is easy. Just dot product is going to be 0. So easily we can find.
So how we calculate? Could you please explain again?
Okay. So this okay. So let me write it here. So we want to construct Q1.
Yeah.
So we have eigenvector.
For 50.
For 50. So for 50 eigenvector is this 50 we have eigenvector 1 2 1 2. Okay.
1, 2.
And we have normalized it already.
Yeah.
Okay. Now we'll find the y1. Y1 is what? 1 upon sigma and A, and here is this V1.
This is what it is. And sigma we know root 50. Okay. A is our 1, 2, 3, 6. And next is this 1 upon root 5, 2 upon root 5.
Correct.
So if you solve this, it would be 1 upon root 5, 250, right? We can make it out. It is going to be 5 root
5
10.
root 10.
And this is going to be, let me erase it. So this is going to be 1, 4, 5. And this is 3, 6 is there. And 3 and 12, 15. So we can make it out 5. So this is going to be 1 upon root 10. And this is 1 and 3, correct? Yeah, 3 and yeah, this is correct. This is our y1. Y1 we got. Now y2 is going to be 1 upon sigma AV2. Sigma is 0 here. So this is undefined. Okay. So we'll not follow this path. We'll choose y2 which is perpendicular to y1. This is our y1 we have found now. And now we want to find y2. So we have to choose which is perpendicular to y1. So how we can choose? So let's assume this is our y2. Let's assume this is our y2. So perpendicular means if you do dot product with his, but this by this one, this y1 which is 1 upon root 10 and 1 and 3, then we'll get 0. 0 means 0, 0 vector. So if it is these two dot products, so let me write in the proper vector form. So let's say our vector y2 is x and y. This is our y, so I assumed. And we have y2 is y1 is already this one we know. This is our y1. Now y2 and dot product y1 is what? Y2 transpose y1. This is how we'll use to do, correct? So y2 is our transpose is going to be x and y, and y1 is going to be 1 and 3. I'm writing this side 1 upon root 10. Okay, this is our y1, and I said this is equal to 0, 0. Correct? This is how it's happening. Now this is going to be x, and x plus 3y will get here. This is what we'll get, and this is equal to 0, 0. Sorry, this is scalar. No, I just missed that. So this will be as finally what we'll get, x plus 3y is equal to 0. Hey, 0, 0 I'm writing. Sorry, this is just a 0. Sorry, sir. So
Sir, you written y2 transpose, so
yes, y2 transpose. Is it wrong? No, this is not wrong. Just a second. So okay, where is that? This one is not clear. Any doubt here? See, generally vector we used to write vertically. Okay, generally this is a general form. Okay, vector we used to write like this. Any vector in vertical form means column matrix. So if you're doing dot product means I just wrote transpose. This is a matrix. Matrix multiplication I'm doing, which is, if it is vertical, if you do transpose, it will be horizontally. Correct? And the second one will be as it is vertical. And this is equal to 0. So this is what we'll get. So this tells you we'll get a linear equation. So from here, x is equal to minus 3y. Okay. So from here, if you assume y is equal to 1, we'll get x is equal to minus 3. Correct? This is going to be, we'll get using this one, we'll get a vector. And this vector is our y2. But let's normalize it. So if we do normalization, we'll get here some normalized form. So this is, let's say, y2 prime. And now finally y2 is, if we normalize it, so this is going to be 1 upon root 10 minus 3 and 1. Is this clear? Is this clear?
Yes, sir.
Okay. This is how y2. Now we are done. Q1 is going to be.
So just one question here. Instead of working it like this, straight away, if the u1 is coming out to be 1 by root 10 1 3, u2 will be obviously 1 by root 10 minus 3 1.
Yeah,
just
correct.
Just change the sign and just transpose it.
Yes, that is what it's usually. If you very much practice, you can directly, without doing very quickly, you can do. Correct. You're right. So this is going to be, now for 50 we are getting for 50 we are getting 1 3. So 1 3 normalized will make it out, the root 1, and this is minus 3 and this is root. So this is our Q. Now this is the SVT. Okay. So we have 1 2 3 6. This is our matrix A, where Q1 is this Q1 sigma Q2 transpose. Q1 is this one, Q2 is, so finally 1 upon root 10. Okay, 1 3 minus 3 1. Okay, and sigma is root 50 0 0 0, and Q2 is Q2 transpose is Q2 transpose, you have to write. So 1 and 1 upon root 5 minus 2 upon root 5, 2 upon root 5, 1 upon root 5. So this is going to be SVT. Clear? Is it better now?
Yes, sir.
Okay, let's do quickly now. The next one is, if you see here, it is the all mentioned it here. Okay, this is the SVT. Let's do one problem on stationary. Then we'll try to. So all of you choose which option is correct here.
0, 0.
Yeah. So this is a easy one. Actually, this is x0 plus y0. Sorry, x square plus y square is nothing but, if you remember, just x square, which is of this one. And if it is in 3D, so x square plus y square is generally this one.
Sir, 0 0.
0 0 is going to be. So here see that this is the minimum point. So generally from the picture it is. Otherwise, if you have x square plus y square, okay. So how we'll get this? This will be done like this.
First derivative.
First derivative. So this is going to 2 and equal to 2. 0 both will give x is equal to 0, y is equal to 0. So stationary is 0 0. So I want to skip some problem because many times same repetitive is there. So minima is this is a maths 2 problem, even no need of it here.
Sir, saddle.
This is not saddle. Why it is saddle? This is 0 is going to be minimum.
Minimum. For this, we should do the second derivative, sir.
No, so for this one, what we will do once we got this one, so we have to find the f of xx and find f of xy. And what is the final thing?
2.
And also f of yy.
2.
2 is more than 0, so minimum.
No, still there is one condition we have to check, right? What is that? The gradient. Sorry, Hessian. F of xx, f of xy, f of xy, f of yy means f of xy. Sorry, f of xx, f of yy minus f of xy square. This should be greater than 0. Means your determinant. This should be greater than 0.
Yes,
If
we are
it is
getting
there,
4
yeah.
minus
If
0,
it is
so 4.
4, this should be, and then if depend on this one, it is 0 minima. Okay, if this is less than 0, maxima. Okay, and maximum minimum, the saddle one is many case. Saddle one is generally here is if it is equal to 0, if this one is equal to 0 or less than 0, these two will give saddle. Okay.
So what was the value of fxy?
First, we have to check the determinant, no? Then we have
Yes. Yes. What is the value of xy?
Yeah, second derivative of fx with respect to y.
So here at the critical point. At the
Oh no, how do we find fxy?
so again, whatever you got this one, derivate it again with respect to x again. So this is going to be 2. And f of xy is anyone, either this one or this one, derivate with respect to, you want to find f of xy, now derivate it with respect to y it. So if you derivate it with respect to y, you'll get 0 because there is no y. There is no y. Okay.
Okay, sir.
So this is a minima.
Just can you show that page, sir? The earlier you have mentioned at the extreme right end, if it is 0, yeah. So if it is 0, we call it saddle point, isn't it?
Mm-hmm.
AC is equal to B square should be saddle point. If less than 0 is, it will be?
Again saddle.
Saddle point. Sorry, since AC is greater than B square, so can you not say it is positive definite?
That is what will come. That is what will come.
Okay.
So if
let's do. Sorry?
if fxx is greater than 0, it's minimum.
Minimum. Less than 0, maximum.
Determinant is better than if
Then why are we finding the determinant?
This is one condition.
Okay.
This is
Both the
this is
conditions
condition.
should satisfy.
Yeah, because saddle one is from determined by from here only. So first we'll check is this critical point is saddle or not. If it is not saddle, then maxima minima. If it is saddle one, which is conditioned by this one, then no need to go ahead. So
equal
here
to 0 and less than 0 both are saddle.
Yeah.
And greater than 0 is always maxima minima, right?
Equal to 0 is to check once. If it is equal to 0, then
I think sometimes
lesser than 0 is fine, but
lesser than
equal
0
to
is pure.
0,
Sometimes
equal to 0 is actually need to further analysis. There is one, see, many things are there. So this 0 1 is, I just no need to write here. It is bad. Mathematically, it is bad. See, if it is 0, no, so in this case of 0, it's actually written, and if you see in a book, you need to do further analysis. Means now it is beyond of, whatever we have this kind of two test or whatever this is steps. Now we have to anyhow try to graph or we have to check is this increasing or decreasing. So some other method we have to follow. So for the lesser one, we can think here is, see, I just wrote many times is actually saddle. So I just wrote otherwise. This is should be the mathematically it should be a further analysis. Okay. Some further analysis we have to. And have to check is this increasing or decreasing, some other way have to follow. So best thing is let's keep it as -6. Sorry, means less than 0.
Greater than or less than. If it is less than, then it is saddle, and greater than, then it is maximum minimum.
Maximum minimum.
Okay.
What is the further analysis?
So many things are there. Sometimes this is 0. What is going to be in this case if this portion is 0? So again, in this case, further analysis is there. Let me check once. Just to give a minute. I'm just maybe I'm forgetting. Let me once check it. The best thing is check. Just a second. For 0 cases, I'm just missing. Uh, if Hessian is 0, degenerate, inconclusive. Okay. So yeah, we are correct. So that is what the inconclusive means. We cannot determine. So for the 0 case, and same is there for if it is equal to 0. So again, we have to do here is also if it is 0 here equal to 0, then further analysis.
So if second derivative is 0, then how can we do third and fourth derivatives? Because the function will not exist. I mean, it will.
So when is minimum?
Minimum means greater than 0. And if it is, what you said?
Sir, I was saying if second derivative becomes 0, then how can we compute third derivative?
So we will not use the third derivative. We'll not use it will not decide. So the best thing is it is inconclusive, and means then we have to do further analysis. Something now we have to use different approach. Now this method will not work. This will not work. Hessian will not work here. Now some try to graph it or try to do thing using the try to first of all parameterize it, think it is decreasing there, increasing there. Something we have to do some more analysis now. If you see in some other book, generally it is written there. And the analysis part is there. Check that it is increasing, decreasing. So see, many times what generally happen, it is determined by the one variable case. See, sometime you are not able to get, but if it is a maxima, here is the critical point. At this critical point, it is maxima. So what will happen? We'll need to check, is this increasing here? And after critical, it started decreasing. So this is a good way. The further analysis generally tells you that before the critical means a interval, suppose A is a critical point. So in this interval, it will be increasing, and A plus epsilon in this interval, sorry, A and A plus epsilon. Here is A and A minus epsilon. In this interval, it is increasing, means this portion I am saying. And in this portion, means this portion here, it is decreasing. So if this thing is happening, then this point is going to be a local maximum. So this is the case when it is one variable. But the same case, the many if you do many practice, if you see some books, another either could be this one, or what is the general thing is people used to parameterize. So if it is two variable, try to change in one variable and then do the further analysis. So it means the work is now harder to the point. The critical point is going to be maximum or minimum. Means we have to do more. We have to some other way we have to follow. So let's leave it. So this is a more.
That is out of the course now.
Yeah, this is out of the course. So no need of it. The best answer is.
In the data science also, it will not require, no?
Not required. Not required, because optimization doesn't need. Optimization means if you are not able to get the optimized one, use another algorithm. That's all.
Okay.
Means another algorithm means, sorry, a different model. Yes, sorry.
Cannot be determined is equivalent to the inconclusive.
Inconclusive, correct.
Right, no?
Okay. Yes. So this is the plot of that. Let's do quickly next problem. This is the same problem. I want to avoid some unique question, because many times I want to finish to solve this. So okay, let's do this one. All of it right. Is this first find the stationary point and decide that is this local maximum or minimum. All of it right. We have discussed a lot on this.
Saddle point.
Easy, we can quickly do. This is a saddle point. You can see it here how it is. Saddle means one portion is tells you increasing, and another portion tells you decreasing. See that how it is. This portion tells you increasing. This portion is tells you decreasing. So this is a kind of subtle meaning of that. We are not in some direction it is tells you know in some direction it is kind of increasing, in some direction decreasing.
Means it is in the direction of x it is decreasing, or
yeah, it's depend on, like, this is a picture of it. So
here
how
in
we
this
get it is,
picture,
so in this picture
x direction, which one is x direction? But it is not given.
not so, yeah.
Okay.
And the method is same we'll do. I think we will get the negative that what is called
How we will get the determinant of this one?
the same way.
Sir, is it maximum?
Determinant is fxs and fxy and fxy and fyx.
No, if it is x square plus y square, we have
Yeah.
f this. F x is going to be minus 2x.
Minus 2x.
And f double x is going to be
Minus 2. Yeah.
F y is going to be 2y.
2y.
Somebody says maxima, let's see it. F double y is going to be 2.
2.
And f of xy is going to be any one of you will take, just derivate it, either this one or this one, okay, with respect to the opposite one. So if it is you are taking this, derivate with respect to y. So this is going to be 0. So Hessian is going to be f of xxx, f of xy, f of xy. It is generally called yx, okay. But here is the same because it is a polynomial. Okay. So in the polynomial case, it is the same.
Normally we write fyx and fxy, no?
This is a, no, so see, this is the same as here. So what is this? This is going to be yy.
Okay.
Okay. Now it is, this is going to be minus 2, and this is going to be 0, and this is 0, and this is 2 here. So if you see, determinant is going to be minus 4.
Minus 4. It is less
So
than 0.
it is going to be minus 4, which is less than 0. So it is a saddle point, the critical one.
And which case we have to take fyx?
No, f of xy and f of yx both are equal. Okay.
Okay,
so
both the same in all the cases. Okay.
In all cases, generally, so this is higher math. Okay, if this is, there is a theorem on this. Okay, so big thing is there. So, but this course it is same.
We can do either take
Either.
y first and then x, or we take x first and then y. No problem.
Correct.
Okay.
Correct.
Okay. Sir.
So let's move on now. The same problem many times will come. I know it. I just want a unique problem. See, this is the same every time is same going to be. I just want to see the still not see many problems exactly same. That what is that definite positive definite? This is what you will say about this matrix. Is this positive definite, negative definite? What we can say?
So what is meant by these terms?
Sorry, negative.
What are meant by these terms?
Positive definite, semi-definite. Are you there when you talk when you don't know the definite one?
No, sir.
Okay. So then okay, let's try it.
A
Otherwise,
option.
sorry, option A.
Yes, sir. Option
Okay.
No,
Positive.
option B, sir.
No, determinant is 0 na here.
Because AC is equal to B square.
Yeah, one of the
Yes, sir. B
eigenvalues is
option.
0.
So it will be positive semi-definite.
Semi-definite.
Yeah, B should be the option.
Correct. So it's a semi-definite. Determinant is 0. We can see one row is dependent on the second one. So it is a semi-definite. And now somebody says what? How will check this? So definite is actually came from eigenvalues. So simply, if you have a matrix, okay, and if you calculate the eigenvalues of it, if the eigenvalues, let's say lambda I, for all eigenvalues, mean to say, if it is 0, then positive definite.
Greater than 0, no?
Greater than 0. Sorry, greater than 0 here is. And if it is this one, greater or equal to 0, then some may not be 0 also. So positive semi-definite. And the case is less than 0. This is negative definite. Okay. And maybe some of them is 0 also. Then semi will be there. Negative.
So
Semi.
if we are calculating A transpose A, then how we can say that it's positive, definite positive, semi?
No. Directly we used to know. Why you are calculating A transpose A?
Sir, your lambda I, what is lambda I?
Lambda is eigenvalue of A. This
Okay,
A matrix.
but there will be two eigenvalues.
Here is 2.
Then which eigenvalue will check whether it's greater?
All. Here for all I.
The common things are there, na? Lambda is less than 0, lambda is less than equal to 0.
Yes.
If it is less than equal to 0, means only one condition will be there, na? Either will be less than 0 or it will be equal to 0.
So here I wrote separately, no? That's why.
So we can write it lambda equal to 0 only, na? Here, because less than I already covered earlier.
Earlier is covered, but I if it is this case only, some of them is negative and 0 also.
Okay.
It is both. It is both actually.
Yeah, for both. Yeah.
The eigenvalues are same, right?
If all, then it will be.
So yeah, this is the actually explaining you everything for all I.
For all I, yes. For all I. For all lambda I.
And maybe if the case is next is indefinite, when some of them, maybe let's say J is greater than 0 and lambda I less than 0. And some of them is greater than 0, some of them is less than 0. Means both you are getting. then this is indefinite.
This is the only case when it will be indefinite.
Okay, so here our case is 2, 2, 2, 2, 2, 2 is there, 2 and 2. So here our this is our matrix. So just find the eigenvalue here.
Eigenvalues will be 0 and 4.
Eigenvalue is 0 and 4. So here the case is becoming this one, greater than 0, 4 is there, and equal to 0 also there. So positive, semi-definite.
Correct.
How did you get 0 and 4?
Means the same as you used to find the eigenvalues.
Okay.
Somebody have calculated and just taken, otherwise
Okay.
do
Yes,
this
I
one.
got. Yes, sir, I know it. Okay.
It's 2 minus lambda whole square minus.
Yeah, correct.
2 minus lambda squared is equal to 2 square. So lambda is plus minus 2 plus 2. So 0, 2 minus 2, 0, 2 plus 2, 4.
Okay, so this is the definite one, and rest all. What is this positive definite? Okay. Okay, here it is.
This is a graph of this one.
No, why this is 14? Okay. Okay, for all.
0, 0. Determinant is 2, B, C.
So there, what is happening? What is f of x, y? It's there. What is happening? You know, right? Are you, last time we discussed, if we have this case, ax square plus bxy, 2bxy plus cy square. We want to convert this in matrix A, B, B,
BC.
A, B, B, C. This is how it is. So our case is this one. So if this is matrix is 2, 2, 2, 2.
So we can check this also, no, sir? AC.
Yes. Yeah. So this is how it is, correct? So
Pardon. This is the standard form of ABBC, no?
ABBC, yes. So we want to find this one. So this is going to be 2 plus 4xy. So sorry, 2x square plus 4xy plus 2y square. This is our f of xy. This is a quadratic one. So what is written here? This says, see, now it is positive definite definition. What is the positive definite definition? Where is that? Okay, here is positive definite definition.
A is greater than 0.
No, only the definition I'm saying.
Definition is greater than
no, definition for this one, for the function one. This should be greater or equal to 0 for all x and y. That's all. What is the definition? This should, there are two conditions which is already hidden here. This should be, first of all, this should be positive for all, and at some point it is going to be 0. These two conditions, which is written here. This is the positive definite case. Now we'll apply the condition there. What are the conditions? When it is positive, the condition are A should be greater than 0, C should be greater than 0. Okay, and next is AC minus B square. That this is what, no? AC minus B square should be greater than 0. Correct? This is what it is. No?
Yes, sir.
Yes, sir.
To check the function, is it positive definite or not? Otherwise,
so
if it is
how does it look on the graph of positive definite?
So the graph is this one has here. This is here.
And if it is negative, it will
So
be
maybe
bigger?
let's see. So yeah. So yeah, the graph is generally, the mean is that positive definite graph means this is the only, means all value is positive and actually passing through 0. So at some point I mentioned no, so this is wrong. At 0 0 it is 0. Okay,
That's
this
the
is what
stationary point.
at is stationary. At 0 0 it is going to be 0. So this is the case of positive definite.
There will be only one point where it will be 0 0.
Only at 0 0 only. Yeah. At origin only.
Other places also be there, no?
No.
It may.
No. No.
Yeah.
It may not.
Yeah, 0 0. Value, the function will be 0 0 at that point.
Yeah, here is you can say it will be 0 when 0 0.
Always it should be only one point at 0 0 at the origin.
Not always at the origin, sir.
No. For positive case, positive definite case always at origin.
Yeah, always at the origin it should be. Then only it will.
It is the definition of positive definite quadratics.
Okay, at xy equal to 0, f of 0 0.
Yes.
And what is the use of this knowing this positive definite and positive indefinite in the practical cases? We are knowing the formulas only, but where it is?
This is used in optimization. This is one technique. Okay.
Further we will use it, no?
Once you know in optimization, what you will see if your function is in two variable, and anyhow you got that this is a positive definite. Sorry, anyhow, you got that it is a positive definite. So it will be automated that 0 is going to be your minimum.
Okay.
This is what is happening.
Yeah. Geometrically it is visible. Yeah.
Visible. So see, this is here. It's simple. Looks like simple. You are doing it two
But
variable.
in bigger problem.
But when it is picture is very big, okay, very large matrix you got. So what is going to be in that case? Yeah. So this is just an interpretation from here to we will conclude to in the machine learning.
In that case, graph will also be not sufficient to understand.
So it will be used in optimization.
Okay.
Okay, so let's move to very quickly to the next problem. So this is a positive definite on many places. So now we have gone through the theory. Let me see. This is a negative one. This is a negative definite. So how it is maxima. Okay.
Okay, so
negative definite. Maxima, correct.
And okay, many problems are the same here. Let's do this problem quickly, and let me know is it positive definite or negative definite.
We will provide the slide.
How will we do for a 3 cross 3? Find the determinant.
Same. No, not determinant, eigenvalues.
Lambda. Okay. So this will be positive definite.
Why?
All the eigenvalues are greater than 0.
What are the eigenvalues here?
Yes, sir. All positive. This will be positive definite.
It's a diagonal matrix. So
diagonal. So that is what I am asking. So it is a diagonal matrix. So
1, 2, and 3. Yes, the eigenvalues are 1, 2, and 3.
Yeah, eigenvalues lie on diagonal. So eigenvalues are 1, 2, and 3, and all are positive. So it is a positive definite. Again, it is a diagonal one. It is a diagonal one. Okay, all are only diagonals only. Okay. Let's quickly do the next. I just want to tell one problem. There is only one problem in solve with this. So very quickly we can do that is important one, PCA. So let me share it once. Just
that is very clumsy also.
No, it is a very I will just tell you one word. You will understand what is this.
Now, solving the problem is easy.
Yeah.
Question on the base algorithm, but the proving the generalized form is very difficult.
So first of all, you can keep remember it. It is an algorithm. Okay, PCA is a algorithm. Okay, see, there is a difference between theorem and algorithm. Okay, so theorem is what? This is a standard thing, means at standard means some result you will get. Some based on some condition will use to get some result. But
Sorry, you're
algorithm is
sharing screen.
no. I am stopped now. Let me share the another. I am just saying that the difference between algorithm and theorem. So algorithm is actually it is an algorithm. It means you will some repetitive work you will do and you will reach to some particular solution. But theorem is some using some condition you generate a result. Okay. So this is a difference. So first of all, you just keep remember PCA is a algorithm. Okay.
Pardon. What difference?
PCA is a algorithm.
Difference between algorithm and theorem?
Difference is algorithm. Sorry, theorem is some you have some sufficient condition and using that you will get a result. Okay, you'll get a result. But algorithms are used to get some approximate solution, not maybe sometime exact solution, but approximate solution. And algorithms are a repetitive work. Algorithms are repetitive work. Same work you're doing many times. That is generally some algorithms. No? So this is a difference. Okay, let me download.
And with prior data, isn't it?
So just keep remember this PCA is an algorithm. Okay, and let me show my screen
So is
first.
it the same as we one study in other course?
Yes, so PCA is you will see PCA is now going to be in MLT. Okay,
First
so
week,
there
not
you'll
second
so
week.
here Prasant sir have taught, but in MLT you will see Arun sir is going will taught, and has very beautifully everything you will explain to. So PCA again you will study in MLT. Okay, here is just brief intro is given. What is the meaning of it? Here is just meaning is given. But in MLT, you will see Arun sir is teaching it. You know already how Arun sir is used to teach. You have seen. We'll see lectures from onward.
In which week in MLT PCA is there?
In starting even. In starting.
Week 1, week 2.
Okay.
But very easy. Very easy. So let me present my screen. It is easy. Okay. Not tough. It is. That's why I'm saying this is an algorithm. If you just do, if you follow the steps, you'll get this.
But here the derivation was some, I think, not clear.
So that is what let me tell you the what is happening. You'll get idea.
Whether derivation part will also affect our examination point of view, or that is not required at all, just to follow algorithms of 5 algorithms.
No, sometimes it's needed. See, if you are in interview, somebody is surely ask. Okay, somebody surely say why this is happening.
Okay.
So you just need to tell this is if you just need to see algorithms are just need to understand. Okay, this is there, this is there, this is there, this is happening. So at least you just understand it. Okay, because if somebody is something is here asking some part is asking is why you are doing. So based on this, if you will follow the next step, your answer should be somebody is asked that okay why you are doing this.
But
So to get this result,
in our MLF, I think only this the algorithm given after the I think PCA, the data and the finding the eigenvalues and then projected data will be sufficient, no?
So here is what is in MLF. This is just here in MLF. It is what is a simple word? What is the PCA? PCA is let me write here so it will be more. Where is that?
The two things are the minimizing the construction error, reconstruction error, and maximizing the conversion. But practically, we are not understanding what is happening there.
So what is happening? So let me tell you. So practically, it's look like what we are doing, but theoretically, what is happening? Reconstruction means you have some set of vectors. Okay, Okay, you have some vectors. Okay, we have suppose some vectors you have. So reconstruction, as the name is reconstruction, we are constructing it again. Okay, so what we are constructing it again? See, suppose this is in R3. Okay, this is a three-dimensional.
Yeah.
So these data are or in R3, and let's say, okay, this is in R3. Okay, fine. Now what we will do? We have three vectors. We'll reconstruct, means again we'll construct using these three vectors. We'll try to construct set of vectors. Again, three vectors will get. Okay, three vectors will construct, but all these three vectors actually will be as this vector is from R3. Okay, three-dimensional space, but the reconstruction will be reconstructed in maybe in two-dimensional, means here not in R2, means maybe a space, okay, which is of two-dimensional. Okay, subspace of R3 which is of two-dimensional. Okay, so we'll getting this after reconstruction. You are getting this vector from this subspace, means reconstruction means previously it is in three-dimensional space, but we change it to, we reconstructed it to in two-dimensional or one-dimensional space. Okay, the simple meaning is, let's say visualization is this part. What is there? Suppose I have two vectors. Okay, maybe three vectors. This is of R2 only. Okay, this is of R2. So we'll apply the PC algorithm. Okay, we'll follow the steps. So once you apply algorithm, you will get again, okay, three vectors. Okay, now see, we know, right, subspace of R2 is any line. So what I am doing, I am reconstructing, and reconstruction, how reconstruct doing? I am actually reconstructing it in one dimensional. Okay, one dimensional. I am sending it back, sending it to, or I am trying to get this vector in one dimensional. Means what? I just, what is that? I think it is embedding something is there. Means anyhow, means when I am applying this PCA, so it will be on one dimensional, means on this line.
Line is two dimensional.
Line is one dimensional. This is one dimensional, right? Line is a subspace of one dimension. Many people, so this is what the doubt. People used to think it will be embedded in R1. Just think that this is in R1. But this is not in R1. You are not doing any. Is this coordinate are changing? No, you are getting the same number of coordinate. Means vectors are of R2 only. But previously this is in, okay, this is in R2. These three vectors are in R2. But now when it is embedded, okay, the vectors you are getting, these vectors are actually from this plane, sorry, this line, which is of one dimensional space. Okay, so this is the reconstruction. So whatever you are doing using a PCA means reconstructed you again the same dimension, means this vector of the same space, but change is there. How I will say that simply, okay, simple thing is there. Again, let me write it here. The another meaning is, the meaning is, let's say these two vectors. Okay, I'm taking these two vectors. These two are independent. Okay, independent vector. So if you do a span here, we take a span of these two. What is going to be? This is going to be vector space. Span is going to be what? This is two-dimensional or not?
Two-dimensional.
These
Yes,
two are
sir.
independent, so you will get two-dimensional. These two vectors are actually.
Yeah.
So what you will say means, you will say these two vectors are of two-dimensional space. Okay.
Yeah.
These two vectors are of two-dimensional space. From this span, these two are. Okay. This is the meaning of saying. Now, okay, I will, okay, project. Let's say project. Okay, for the time being, I am projecting these two vector in, okay, on a line of R2. I am projecting on a line of R2. Okay, which is, let's say this line is generated by one vector. Okay. So what is happening when I embed it? So this line is actually this line is in R2, fine, but line is a one-dimensional space. Line is what? Line is a one-dimensional space. This is a one-dimensional.
Yeah, for vector point of view, it is one dimensional because the
one dimensional.
For a vector, a line is required at least for the direction, right?
Yes.
That's why, no? Because if it is a single digit, then it is
one vector. One vector is needed to get this line. This one vector is enough.
Yeah.
So you are projecting for the time being. You are just projecting these two vector. You are projecting on this line. That is what your PCA does.
Dimension, yeah.
Means you are reconstructing. Means from a big dimensional space to you are reducing its dimension. The meaning of
this line is of R2, no?
In R2 only. R2 only.
In R2,
on
was
this
dimension
space
is
here. One.
Dimension.
But dimension is one. See it. From R2, this is two-dimensional. Sorry, where is that? So this is two-dimensional.
That means it's a plane. A two-dimensional means it's a plane.
Generally you can think. Yeah, from plane. From plane to you are projecting on line. So this is a PCA is not projection. It is an algorithm. So in layman word, I am saying it. Okay, simple
but
word.
Two-dimensional cannot be plane, no, sir. Two-dimension has to be a Cartesian x cross y. For plane, you have to make third dimension, x, y, z. Plane cannot be in two dimension. Plane requires a third dimension.
No. In two-dimensional plane will be there. Why not?
How can you put a plane in two dimension?
X, y is a plane.
Which one? X, y is not a plane. If you don't get the z dimension, you can tell x, y is it's basically if z is 0, then you can say an x, y is a plane. You have to say z is 0. Otherwise, you cannot say this is a plane. Without the third dimension, you cannot say this is a plane. In R2, we cannot say.
So there is many things are there. Yeah, you are right. And also he is correct that sometimes. So saying to be XY plane is what we used to say.
Sir, that was automatically assume ki z is 0. Plane we have to actually first it start from 2D dimensional. 2D dimensional means x and y, that's a plane just like a screen. Then we go to the 3-dimensional, and in the 3-dimensional we convert 3-dimensional into 2D. So for that case we can say that z is 0. That becomes simply 2D.
Exactly.
That's the logic. It's not like mandatory ki c should be 0. In every
Basically, how are you projecting? You can, if it is your two-dimensional data, if you project it on a straight line is basically what? Straight line is not a plane.
A straight line is the part of the subspace of that plane only, because that straight line will be in a plane, XY plane. If there is no z dimension, that will lie on a plane, XY plane.
I'm saying XY is a plane, but it's a special plane in which z dimension is 0. So if you assume z is 0, then we can tell. But my simple question is...
That's also the correct logic, sir.
Both things are correct.
Yeah, actually it is hidden part is that. Hidden part is that.
Due to this confusion arises because
due to this it's coming.
In that way,
so actually, what is the question? I just joined now. Can you sir tell me what is the question?
Question is R2. We are saying the line is in R2, but line is in one dimension in a vector space.
No, so if it is this confusion, no, let me remove this. So said thing we have two planes. So let's say this we have two XY plane. Okay, we have two XY plane. The vectors are here. Okay, I am projecting on this line. That's all.
Yeah.
This is by this way. I think this is a good. I have another.
This is better. This is better.
I have let's say another. Okay, so I have two vector. This on this plane here. I'm projecting to the another XY plane, which projecting means one-dimensional space here on this line. This is PC.
So when you project it as a point, you project it at a point.
So projection means the PCA is not only the projection. Okay, PCA is not a projection. So no, so you are saying the point means I am thinking this. So previously I was thinking this vector in R2, But now same way I'm thinking these vector in just on line.
Both on the same line.
Same line. Just think that now we are on
Line
only on
line
lines.
is
We are
also in
thinking on
R2.
lines.
Yeah. Line is also in R2.
Line is R2 fine, but think it is this is a one-dimensional space.
Yeah.
Line is one-dimensional.
One-dimensional
Space.
And R2, this R2. So what is difference between this R2, the vector space R2? What is difference between the line R2? This is the confusion.
So for the timing, just say that what is happening here. I have some set of vector in higher dimension, okay, some higher dimension R2 or some higher dimension, and now anyhow, so in machine learning, what it does, it does that I have some more features, okay.
Suppose we are progressing from R4 to R2, then it will be clear. Suppose it is
let me tell you in the machine learning case what is happening.
Please.
Suppose we have some set of features, okay, as you know, price prediction of a house, okay, price prediction of house. So it have some size of the house, and another is the location of the house.
That is okay.
And another thing is let's say the house is haunted or not, okay. Let's say third feature is house is haunted or not, okay.
Yes.
This is these three features I have.
Yeah.
So many people what does, or maybe haunted is fine, okay. The another thing is, let's say number of people living, okay, some other rooms are there, number of people living some other rooms. Okay, this is another feature of the some building in a room. And another is, maybe let's say another is haunted or not, okay. These the four features I have. So is this feature is important? How many people are living? Is this important?
No.
Not important.
Not important.
The important thing is location, okay, size, location, and maybe haunted or not. This may impact this may also impact. So these three features are important. So what is happening? So previously it is in 4-dimensional. See, it is saying to be this is in 4-dimensional. These three these features are actually, you can say this is a 4-dimensional.
4-dimensional.
But now I reduce in 3-dimensional. Only three things I am considering.
Is this dimensionality reduction?
Sorry.
Dimensionality reduction. Is it the same?
No. So dimensity reduction is different thing. There you used to convert the vector in from. See, you used to convert 3-dimensional vector into this one, in 2 coordinates are there. Okay, but here the points are not changing. How many coordinates are there? It is not changing. Okay, it is not changing. The vectors is reducing. Means direction is reducing.
Okay.
Here these features are called direction. Now direction is reducing. Of features I am reducing. This is what it is. Sorry for some background noises going to be. Let me mute for all time. Then we'll continue. So our side is marriage, no?
Sir, I have one query actually, other than this topic. Sir, is there any chance that the deadline of week 7 will be extended for 1 or 2 days? Because we have other subject also, so difficult to manage.
I cannot take decision even, so it's generally here. So very less chance. If it is
very less chance.
Yeah, if it is, it should be. If it is already mentioned that is extended, so it's already extended. So why we are waiting for that?
No, sir, it's not extended. It's like previously we both 6 and 7 have same deadline, 7 March. Oh, sorry, 2nd March.
I'm not sure. I will not even give surety that it will be extended.
Although it was a difficult part, but still it fall under the after the quiz 1, so we are facing difficulty.
Yeah.
Yeah, both 6 and 7 both come. So like I have multiple subjects, so that's why.
But questions are not so difficult. I think theoretical part is difficult.
Yeah.
So the thing is clear here. Okay, so is this clear? What is PCA does? PCA is actually kind of reducing, you know, the you can think as, you know, this is reducing the features. Reducing the features means from
without distorting the data points.
Yeah.
Right, no?
Sorry.
Without distorting the data point, it is reducing to the.
See, it is not affecting much. This portion, this how many people living, it is not affecting much. Maybe some person would be there is actually used to want a big, good society. He will look at, but this is not a crucial. This is not important. Just a part of it, but not important.
Correct.
This particular, it is haunted or not, this has to be, dropped. These decisions, so this is for 4 features, so it is easy. If there are 1,000 features, how the computer decides which one to be?
Computer. So that is what is it's reduced the dimension, means it removes some features which is not important. So see,
Who will decide which one is important?
Yes, how they will decide? That's my question. So
computer will decide, or the
because human being cannot decide out of 1,000.
So see, deciding. So this is just a starting. You started. Sorry, you started MLF now. So let's move ahead. Okay, so let's do MLT. Let's do MLP. Then you will see there many things are there. So many things are there. So many features are there. See, you at the end you will not do. You will just import a library. Okay, a scalar, and just write PC some one line of code you will write, and you will do that PC. Okay, but interviewer is, he wants to know, okay, you use this model, how this model works. This is what it is. Otherwise, so many libraries are there in Python already. You used to it. NumPy, other library you used to already. No, you are using it in the Python. So similarly for machine learning, there are so many libraries are there. You just call them and write one line of code. He will do the PC. That's all.
Okay.
So any dimension data is reduced to a line projected on a line.
So it's how it's reduced. So that is what in the PCA is where we used to reduce. We'll choose that eigenvector which have the greatest eigenvalue.
Can you repeat, sir? Which has the greatest
eigenvalue?
Greatest eigenvalue.
Greatest eigenvalue.
Okay.
So not only what it does, we are not only see. So this is a reconstruction we are doing, no? So many problems are there. This PC is very important algorithm even. See, when we are reconstructing in some another vector, okay. So I want to reconstruct such a way that errors should be lesser. Okay, this error, okay, this differences between these vectors means original one and new one, the error should be lesser. So how I can get this lesser error? The way is that, okay, do PCA or okay, what is that projecting or PCA are doing on one dimensional, how that one dimensional vector you are getting, the vector which is okay, the vector eigenvector which have the greatest eigenvalue, I will choose that eigenvector, so that if you do the reconstruction, it will give lesser error. Suppose I have, okay, for example, let me, all of you know, didn't get, okay, this is the vector I did PCA, and okay, a reconstruction I did in one dimensional space. Okay, one dimensional, fine. But what is that dimensional? What is that space? So that this reconstruction, the new one and the older one, if you subtract, that is, you will get error. How I can reduce that error? What is going to be this space? How will get this space? So to get this space, what you will do, you will find using this, what is that, you will construct a matrix. Okay, you will construct a matrix here using this vector. Okay, and some A transpose, a covariance you will find. Okay, covariance matrix you will find, and then after you will find the eigenvector of that covariance matrix you will find, and then find the eigenvector and choose the greatest eigenvalue, okay, and eigenvalue of that. Okay, eigenvector of that. This eigenvector, if you write, okay, span of it, okay, span of eigenvector, it will be one-dimensional space. Project there, and by this construction, you will get lesser error. This is what the PC. See the PC. Okay.
Can we say that the higher the eigenvalue, more the important of that dimension?
Yes.
Is it so, no?
So higher the eigenvalue not means I want to some data I have, whatever the eigenvalue to keep, choose the greatest eigenvector. Okay.
Why we choose the greatest? Because what I'm telling is that, or another factor is also there, because the higher the eigenvalues means that factor, that dimension is more important for the.
That direction is.
Am I telling you that is correct now?
Yes. Suppose you have, for example,
suppose we are taking 4 dimensions out of 100, then the 4 highest will be more important. Is it so, no?
4 highest.
Suppose we are reducing to 4 dimension from 1000 to 4. All the 4 decreasing 4 values which are higher, it means that these 4 dimensions are more important. Is it so?
Yes, these 4 dimensions are important.
Okay.
So suppose you have what you will do in that case, you will choose the lambda 1, lambda 2, lambda 3, lambda 4. Okay.
Yeah.
And you will choose in this order.
Yeah. Correct.
Means greatest one.
Yeah,
and eigenvector corresponding to, let's say, V1, V2. This is V3 and V4. Okay. And now how it is? Find the span of V1, V2, V3, V4, and project the 1000 vector to here.
Yeah.
That's all. If you project it, the reconstructed vector you will get, and whatever the reconstructed vector, 1000 reconstructed vector you got, if you
will have the less reconstruction or higher the variance.
Higher the variance.
Okay.
That's all.
Correct.
So PCA does 2 work. What are the works? It reduce the reconstruction error and maximize the variance. Okay. I hope is it clear? PCA, the
what do you mean by maximizes the variance?
Maximizing the variance, I see. This thing is a bit even I have some confusion. The maximizing variance is, see, sometimes in the statistics we want, the best curve is what? The normal curve, right?
Yes.
Generally we use
normal distribution.
But normal distribution. But the maximizing variance means is meant like this it is. But if it is this case, then why? What is the meaning here? I just need to even I see it. Maybe it is, it machine learning.
Then I think all the points are around the same. When you maximize, the curve becomes flatter.
Just I will confirm it. Actually, I didn't. You just asked, then I got this. So I will confirm this later, but this time I will not sure this. Okay, I have to search even that why. So this is the mathematically I know it. We are getting the maximum variance, but how it's impacting on machine learning is still remain to, I have just searched it and will let
that's
you.
one question. The maximum eigenvalue, will it give the maximum error, or it should not give the maximum error?
No, maximum when you give the lesser error, no, in comparison.
That's what I'm saying. That the minimum, the least eigenvector will give the maximum error.
Correct. Not maximum error. Not necessary. You can do some apart from the vector.
This reconstruction error is same as the variance, projected variance or something like that. Reconstruction error. This reconstruction error is the mod of xi minus the what do you call the projected value, isn't it?
X bar.
X bar. Sorry.
Not x bar. It is x tilde. So xi minus x tilde mod square should be the reconstruction error. This is as good as your variance, no? Projected variance.
So no. So projected variance is different thing. No, variance we used to calculate by greatest eigenvalue. Greatest
No,
eigenvalue give that is your variance.
no, that's
Variance is
basically the root over of that, square root of that is the sigma you are saying, na? That that is
variance.
if you say projected variance, what is the meaning of projected variance?
Projected variance is where it is written. Projected variance.
I don't know. Somewhere I was, one what do you call it? One such lecture. I think it is mentioned. It was I'm not able to recall one such session.
Projected variance is nothing but just a variance, because here in a PCA we used to project it. So that is that is a different. I mean, variance, projected variance is variance, you can say.
Actually, projected variance is same as variance itself.
It's variance. The reason is what we in PCA do, we used to do projection. Okay, what we used to do here in PCA, we used to do projection. See the formula. But projection is a very different. Like we used to project an eigenvector, and also if you see it formula, what is a PCA definition? Projection formula, and the projection formula is see this formula.
Yeah. This one. Okay. So this is the projected variance is nothing but the lambda value. Lambda 1 is equal to 3. So
This is a slightly different projection. We are not skipping the other vectors. This vector is also included.
So this is projected variance is 3 and the reconstruction error is 1. So how this lambda 1 is coming out to be 3, sir? Actually, this one. This is the same as lambda eigenvalue 3.
Eigenvector, yeah, eigenvalue.
Okay.
Eigenvalue.
Covariance matrix.
Yes. The covariance matrix, you will get the eigenvalue, which is 3. 3 is the maximum one. So the projected variance is basically the eigenvalue.
Yes.
Okay,
easy. So don't be confused much. This is good even. I hope you understood the intrinsic what is happening in the terms of linear, machine learning case. Yeah, somebody's want to say something. Yes.
Sir.
Yes.
Can you show that eigenvector thing? I just wanted to ask, how did you compute that 110, all those terms?
110.
110.
Yeah, this one.
Yes. No, in that PC.
Yeah, this is what.
This thing.
Yeah, this is what. Here it is. Let me see it again here. Here it is.
Yes, sir. How did we compute this?
This is just eigenvector. For lambda 3, this is eigenvector. This is eigenvector. Once you got the eigenvector, what you will do? The projection of x1 on u1. u1 is your eigenvectors. x1 is your original data. u1 is your eigenvector. So project on there. This is what you get.
What is matrix A here?
Matrix A is your covariance matrix.
Okay.
Covariance matrix is how you got. See, it is.
Yes.
Okay. Way to get. Okay. So projection is on this. You projected x2.
How do we find the eigenvectors when the matrix is a 3 cross 3?
Eigenvector?
Yes. Now, when the matrix, this is a 3 cross 3 matrix.
So how I got 3 cross 3 matrix?
A is 3 cross 3, no? The covariance matrix.
Covariance matrix is 3 cross 3.
Yes. So the eigenvectors, we have to do factorization and find.
No, how you used to find it? Now the way you know to find eigenvector and value, that is the only.
Okay. Yeah. No.
This characterization is the characteristic equation.
Yes.
A minus lambda.
That is to find the eigenvalues. Yes.
Yeah, eigenvalue.
Yes. No, eigenvalue becomes hard, no, sir, here in a 3 cross 3.
It is generally hard, but it's depend on how it is asked.
Yes.
Okay. So I will try to provide you this PDF. And this is the covariance I actually want to tell. I hope, I think now is it clear? Bit better at least. Not all, but at least something is clear. This
Yes,
PCA.
sir.
Yeah, conceptually it is clear.
So now just try to even, I will just wait. Let me give you this slide even. This is a PDF, no? So
Please give the slide. So
let me
then
provide here itself both slides. So just a minute.
solutions are also there in the slide.
Slides solution also there. So just a minute.
Sir, will it be uploaded in photo?
Do you have some question bank and solution bank also, sir, for this 5, 6, and 7 weeks? Because without practice, it is very difficult to catch. So do you have the question and solution both?
Both for of PCA?
Not PCA. Week 5, week 6, and week 7. All the 3 weeks questions and answers, so that we can do more question. Because without doing it is not possible. Different type of questions to solve, because the concept is 100% not clear. We understand, but suppose the question is twisted, then it is very difficult to get inside. Got my point? Suppose it is given as what you just we solved it. Now it is a straightforward question, just given, find a step by step. But in the examination it does not happen. In between. So such type of collections we will do, then it will be, I think it will be better for us, because this is difficult part. Linear algebra is difficult part. Without practicing, it is not possible to we will do practice, then we will go again to the theory, then it will be easier. I think so. So the question is required to solve, then we will go to theory again.
So yeah, anyhow I have to look at.
Yeah, because one time it is not sufficient to get it captured.
Yes.
What I learned is, because I did it, but 100% not sure. So somewhere confusion is there. Some derivation part is difficult, but at that point when we do some questions, then we will go to the derivation, that it will match with that, perhaps.
Correct.
It will be easier if you provide us the questions and solution week 5, 6, 7 only, not others, because others are independent. We will do it. These 3 things are
okay. So
suppose it is in the PYQs, then it is very difficult to go there and search there which one is week 5, which one is week 6, But whatever it is collected, then we will do it. First we will do it by seeing also solution, also no problem. But after that we will touch the another questions.
Yes. So let's say how it could be this time is.
If it is possible, because you must have some collections for that. So we will do that. Time is also important. So many things are there. So first it is required to capture the concept. Then we attack to the questions, different type. We are not confident to attack the question, any question. We are just doing if the same type of question, then they will attack, otherwise leave it.
Correct.
That is not the way to, I think.
Well, okay, so I will tell.
If it is there, then just provide it, we will do it, no problem. No lecture is required. In the revision session, we should be confident.
Yes.
Otherwise, we will always ask in the revision session, always confusion will be there.
Yes.
Am I right?
Okay, so yeah, correct. So the thing is, okay, actually last time one person has also asked. Okay.
I think it is there, but collected is not there. Somewhere it is there. But what happens? We go to the week 8, then we forget 5, 6, 7.
Actually,
and then quiz 2 comes, then again we are in the same boat.
Are the solutions of quiz 1 available anywhere, sir?
Till now, I don't think. Till now, I don't think it's already okay. Till now, I don't think it is available. We will say to it will try to provide it. And the first thing is I have given the both link, in this chat. First, I just keep it note. Which one is also provided. Yeah, just now in here in the chat here.
Okay.
So at least who is here can take it. Let me.
Sir, how to download this periodic slides?
The first
Periodic.
link, can you please share it again?
First link.
Yes, because I joined a little late.
Okay. Okay. So all of you able can see that.
This
is week
part is
7.
very interesting. I think it is interesting to learn, but confidence is required. Then only it is useful. Otherwise, I think after in going to MLT, it will create problem. I think so, because the same thing will utilize there. I think so, because these are the only theoretical part. At that time, you will not be confident. Then it will be very difficult to implement it.
Yes, VT and this PC, okay. Okay, we'll check it. Okay.
Okay, if it is possible, sir, then please provide us.
People have even asked. Okay, I will think it even.
Okay, sir. Thank you.
Yeah.
Even though you don't have so
Thanks,
much
everyone.
time, but this part is very important.
Yes.
Okay, sir. Thank you.
Yeah.
Thanks.
Week 5 and 6. Okay. Okay. Thanks, everyone. Try to do it. Okay. I hope it's a bit clear. Thanks, everyone.
Thank you.
Thank you.
Okay.